everyone, welcome back to my channel. Today we're going to be solving a video in which we have to find the half-life of A and of the type reaction where 2 moles of A react to make 1 mole of product P. This is a first order rate decomposition, and then the rate constant is given over here, and then we will also find the final concentration. So let's get started. Since it's a first order reaction, I can write the rate of reaction R is equals to the rate constant K multiplied by the concentration of A to the power of 1, because this is the first order reaction. Okay, now let's write the equation for the rate of reaction in terms of concentration. So we can say over here 1 mole of production of P is equal to half the rate of consumption of A, because 2 moles of A make 1 mole of P, and there's a negative sign over here because A is consumed. There's a positive sign over here because P is produced. Okay, so we obtain these two expressions in R, this and this over here. Okay, and then we can isolate the A term. So like let's take this side, the left hand side of the equation, and then let's take the right hand side of the equation and like make them equal to each other. So the equation is in terms of A. Now we obtain this equation over here, this here as well, and then let's do some separation of variables. So I take dt on the other side, and then I bring A on the left hand side, and then I can safely integrate them. So let's talk about the limits of integration. The time is going to be from t to 0, and the concentration is going to be from A at any time A to A naught, which is A initial. We integrate them. This is the result we obtain, and this over here is our final equation for the concentration profile of A, which says the log n or ln of A at the concentration at any time, and then this ln A naught is the concentration initially at times equals to 0 is equals to negative 2 kt, and k is the reaction rate constant. We do a little bit of algebraic juggling over here, and then we reach this spot over here. And since I'm trying to calculate the half-life, so what is the half-life? Half-life is any time where A is actually half of the initial concentration. So half of the initial concentration, this is going to be 0.5 A naught. Okay, so I write it this way, and then I can see that A naught can just get cancelled, so I obtain this expression over here. Okay, and then I have written t half over here just to indicate that this is the time when half-life occurs, and this is my expression for half-life. Normally, if we look at textbooks or maybe in your previous knowledge, you'll say t half is equals to ln 2 over k, but in this case we know it's ln 2 divided by 2k because of this stoichiometric number over here. Okay, now let's tabulate our half-life, and like we can have a numerical solution for it over here. So ln 2 can be evaluated. K has been given in the question over here. Okay, I'm just going to insert the value of k, and then I got the half-life. Now let's go to part 2 of the question. So it says what is the pressure after 50 seconds when the initial pressure is 33 kilopascals. So since let's say my reaction is like a gas-phase reaction. So in cases of gases, I can equalize pressure to concentration. Okay, so for ln A naught, I'll just substitute 33 kilopascals. So I can just substitute 33 over here. And this was the main equation I obtained for the concentration profile a few seconds ago. Let me make A the subject of the formula, did some algebraic juggling over here, and in place of A naught, I put 33. In place of time, I'm going to place 50. And A naught 33, in place of time, I'm going to place 50, and K is given in the question. And then this is how I obtain my answer. Now let's go to part 2. Part 2 says 20 minutes. And if we look up, the units of K are second inverse. So it means it's second. So I'm going to convert 20 minutes into seconds. Hence, I multiply 20 into 60 in place of T. Okay, and this is the expression I obtain. So one nice trick to see over here is that this is the answer that I obtained. So initially the pressure of A was 33 kilopascals. After some time it becomes 32.998. So this is because A is decreasing because it's getting confused. It's getting consumed. It's getting consumed a little bit in part 1, and it's getting more consumed in part 2 as time passes. That's all, and thanks.